case of a sinusoidal flux in a coil. We begin with coil, that coil, and we apply a sinusoidal function of time, a voltage source with this value, peak value √2 VRMS. It's a cosine, the frequency omega radians per sec. As soon as we apply that voltage there, a current flows into the coil, and that current will create a magnetic flux of so many Webers. The flux will induce, according to Faraday's law, a voltage E across that coil. That voltage, because of Kirchhoff's voltage law, must be exactly the same as the voltage applied by the source. √2 VRMS cosine omega t, exactly the same. That voltage, as I said before, is a Faraday's voltage. But because of the polarity I gave to E of t in the figure, I don't need to put the negative sign of Lenz's law. That is sufficient. Those two equations allow us to solve for the flux in that coil as a function of time. Check it out. I equate them. I divide both sides by n and integrate on both sides. What is the integral of the cosine omega t? Is it sine omega t divided by omega, right? That's correct. Now check it out. The flux is also a function of time. It has a peak value that depends on the RMS voltage of the source we're applying. It depends on the number of turns of the coil, and turns depends on the frequency of the voltage source we're applying, omega, and it's a sine. The voltage applied, the voltage induced, and the flux that appears inside the coil. Observe, the flux is a sinusoidal function of time that has a peak value. We can solve for the RMS voltage induced in the coil like this, and even that constant 2 pi over √2 can be approximated by 3 digits like so. 444 Fn, the peak value of the flux. That is the famous 444 formula used by electrical engineers to find what is the RMS value of a voltage induced in a coil of n turns by a sinusoidal flux with a peak value of phi peak. We obtain the RMS value of the induced voltage in the coil as a function of the peak value of the flux that is oscillating sinusoidally inside the coil. The original voltage that is applied and the voltage that is induced in the coil is a cosine. The flux as a function of time is a sine. That means that the flux is lagging behind the voltage by 90 degrees. The flux lags behind the induced voltage by 90 degrees. I sub m is the magnetization current, the current responsible for the creation of that flux. The flux that appears there, the flux that is a sinusoidal function of time. If we divide that flux by the cross-section of the flux, assuming that there is iron in there, we get the flux density, which is also a sinusoidal function of time. And if we divide that sinusoidal function of time by mu of the iron, we get what is the magnetic field as a function of time. If we multiply that h by the mean length of the trajectory of the flux inside the magnetic circuit, we get what is the MMF applied to the magnetic circuit by that magnetization current in those n turns as a function of time. And if we divide that MMF by the number of turns, then we get what is the value of the magnetization current. Please observe the magnetization current in this context, where we are assuming that the permeability is constant, is also sinusoidal. More. Observe, the flux is a sinusoid. The current, the magnetization current, is a sinusoid that is perfectly in phase with the flux. The magnetization current is in phase with the flux as a function of time. And because we have seen that the flux is lagging behind the induced voltage by 90 degrees, then that means that the magnetization current is lagging behind the voltage induced in the coil by 90 degrees as well. That makes sense. It's an inductor. Now we have two coils. Coil 1, coil 2. The first one has n1 number of turns. The second coil has n2 number of turns. And we apply that sinusoidal function of time to the first one. Of course, a current flows into it, a magnetization current that I'm representing with a phasor. That one will create a flux. And that flux will induce a voltage E1 in the first coil. I'm representing that also by a phasor. The value, the RMS value of that phasor, is given by the 444 formula. That is 444 frequency 60 Hz in Canada, number of turns N1 multiplied by the peak value of the flux, whatever that is. And the same flux is inducing in the second coil another voltage, E sub 2, represented also by Phasor. The RMS value of that is given by the 444 formula. The only difference with the first one is the number of turns. If we find the ratio of them, we realize that one of them is related to the other as the number of turns in those coils are related to one another. This is the seed, the beginning of an AC power transformer, but there is lots more that needs to be talked about. Now, because there is a voltage there, we connect a load. Let's begin with a very simple load, a resistor, like that one. As soon as we connect the resistor, a current flows like so. A phasor, I sub 2. That current, because the load is a resistor, will be in phase with E2. That's correct. But look, originally, before we connected that resistor, the only MMF in that magnetic circuit was N1I1. In other words, it was N1 magnetization current, and that was the one responsible for creating the flux 5 sub T. Now we have the current I2 that is applying another MMF, N2I2. And being less long what it is, that N2I2 will oppose the original MMF N1I1, and we end with a total MMF on that circuit that is N1I1 minus N2I2. Observe that I don't call the current in the first coil IM anymore. I'm calling that I sub 1. If we allow that I2 reduces the MMF to that magnetic circuit, the flux will be reduced as well. But that is impossible because the induced voltage in the first coil depends on the flux. And that voltage cannot change because KVL in the loop on the top of the figure insists that that voltage must be equal to the value of the external source. So you see, E1 cannot change, the flux cannot change. So that means that the MMF total cannot change. It should be N1 I magnetization. That means that I1 is not the I magnetization anymore. No, it is more like this. The current in the first coil has been increased by value I2 prime, so that the combination with the magnetomotive force applied by the second coil gives the same MMF that we had before we closed the switch on the resistor on the second coil. Who is I2 prime? I2 prime is what we call the current in the second coil referred to the first coil, that value over there. Let's put all together. In the first coil, that phasor represents the voltage induced and the voltage applied by the external source. The magnetization current is 90 degrees behind that as a phasor. And the current of the second coil refers to the first one, this one, I2 multiplied by N2 divided by N1 is in phase with that voltage. Why? Because E1 is in phase with E2. Why? Because both of them are induced by the same flux. Both of them are proportional to the derivative of the same function of time. Of course, E1 and E2 are in phase. And I2 is in phase with E2, so I2 is in phase with E1. The current in the first coil is a combination of the blue and the red current. This is the actual current in the first coil. Pythagoras. Now, time for a tutorial. We have that configuration. We have two coils. The magnetic circuit in the left was built out of sheets of ferromagnetic material that have a constant permeability, well, that's a dream, of 6,200 times the permeability of air. The stacking factor is 76%. What is that? Well, out of the cross-section that we can compute there, 2 centimeters multiplied by 3 centimeters, only 76% of that is iron. The coil on the right has 15,900 turns. The coil on the left, A, has 3,200 turns. Assume that all the flux is in the magnetic circuit and it's contained within the ferromagnetic material. That is a way of saying there is no magnetic leakage, there is no flux outside of the iron. We apply a sinusoidal voltage signal to the coil on the left, directly out of a busy hydro residential power outlet. That is RMS volts, 120, frequency 60 Hz. So that is the problem. Observe the dimensions. It's almost square, but not quite. The first question is, what is the RMS value of the current in the coil on the left? What they're asking us is the magnetization current. Let's find it. To find that current, we need the total MMF needed, right? That's right. To find the total MMF, we need the total magnetic potential drop. To find the total magnetic potential drop, we need the value of the magnetic field in each one of those legs. To find the magnetic field, HFE, we need the flux density. And to find the flux density, we need the flux. How can we find the flux? We have a very important formula. We know that the RMS value of the voltage we apply, 120 volts, is dependent on the peak value of the flux, like so. So there we have a formula. 120 volts induced voltage in the first coil is 444 times 60 hertz times 3,200 turns multiplied by the peak value of the flux, and that is the peak value of the flux in that core, 141 microwebers. If now we divide that flux by the cross-section area, that is 0.02 meters, multiplied by 0.03 meters, multiplied by 76%, that is 309 milliteslas. That is the peak value of the flux density. If we divide that by the permeability, which is 6,200 times 4 pi 10 to the negative 7 henries per meter, we get that the peak of the magnetic field is 40 amperes per meter. The total MMF is that magnetic field 39.6 multiplied by the total length of the trajectory of the flux, that is 2 times 0.14 meters plus 0.15 meters. Divide that by the number of turns of the coil, 3,200, and we get that the magnetization current's peak is 7.2 milliamps. And the RMS value of that current? Well, divide by root 2, 5.07 milliamps. And that is the answer. That is the RMS value of the magnetization current in that coil. Now, second question. What is the RMS value of the voltage induced in the second open coil? That's so easy, right? We know this. The ratio of the RMS values of the voltages induced in both coils are given by the number of turns. So, the RMS value of the voltage induced in the second coil is 120 multiplied by the number of turns, 15,900, divided by the number of turns of the first coil, 3,200. So the RMS value of the voltage in the coil on the left is almost 600 volts, still low voltage. Third question. Now connect a resistor on the second coil, the coil on the right. A 44.5 kilo ohm resistor. What is the RMS value of the current in the first coil? We know that's going to be bigger than the magnetization current, right? Let's compute that. That current in that resistor will be the induced voltage, E2, divided by the resistance, 44.5 kilo ohms, that is 13.4 milliamps. The RMS value. If we refer that to the coil on the left, how? We multiply that by N2 divided by N1, and that is I2 prime. RMS still, because R2 was in RMS. We get 66.6 milliamperes. But those 66.6 milliamperes are in phase with the voltage, while the magnetization current is at 90 degrees behind the voltage. So the current in the first coil has a value as a complex number that looks like that. If we give a 0 degrees phase of reference to the voltage induced in the coils, then the current is like that. Real part, 66.6. Imaginary part, negative 5.1 milliamperes. The absolute value of that is going to be the RMS value of that current, which is 66.8 milliamps. That is the answer. The RMS value of the current in the first coil with that resistor connected is 66.7 milliamps. And that, my friends, is all. Thank you very much for watching, and I hope to meet you again in the next video.